Good morning, dear students. Good morning, students.
Good morning, sir.
Good morning, sir.
Morning, sir.
Good morning, sir.
This is your physics class.
Good morning, sir.
Good morning, sir.
Very good morning. We are going to discuss some of the example problems which are related to the center of mass of 2-point masses. So, before starting the class, I am going to mute your voice so that there won't be any disturbance for others. Kindly follow. Fine. What is the center of mass? The center of mass of a body is defined as the point through which the entire mass of the body appears to act or appears to be concentrated. So, center of mass of a body is defined as the point where the entire mass of the body appears to be concentrated or appears to act. So that center of mass refers to the entire body. It represents the entire body. Based on center of mass of two bodies or 2-point masses, there are so many number of problems, example problems. We are going to see 3 problems here related to center of mass. First one, before going to the problem here, you would have come across these formulas. Suppose when the masses are on the positive x-axis, we shall go on with the formula first. When the masses are on the positive x-axis, when the masses are on the positive x-axis, then the center of mass formula can be given by xcm is equal to m1x1 plus m2x2 divided by m1 plus m2, where m1 and m2 are the masses of 2-point masses and x1 and x2 are the positions of the 2-point masses from the origin. You would have seen the diagram. Second one, when the origin coincides with any one of the masses, when the origin coincides with any one of the masses, when the origin coincides with any one of the masses, there the formula goes like this. I am writing you the simplified version of this formula. Xcm is equal to, if the mass m1 is coinciding with the origin, then the formula becomes m2x2 divided by m1 plus m2. m1 x2 divided by m1 plus m2. This is the formula for center of mass. Because you are going to use these formulas to solve the problem, so you should know. And the third one is that when the origin coincides with the center of mass itself, when the origin coincides with the COM, COM stands for center of mass itself, then what is the formula for the center of mass of the two bodies? We can write here, and we can see here. Here, principle of moment comes into play. Principle of moments comes into play. We can write it as m1 x1 is equal to m2 x2. Actually, this is principle of moments. The sum of the clockwise moments is equal to the sum of the anti-clockwise moments. Principle of moments states like this. the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. So you will be getting the principle of moments condition over here when the origin coincides with the center of mass itself. So three conditions are there. With that, we are going to step into the problems now. We shall see. Example problem, example 5.1. Let me start with example 5.1. Two point masses 3 kilogram and 5 kilogram. Actually, they are given 2 point masses 3 kilogram and 5 kilogram are at 4 meter and 8 meter distances respectively. X1 is equal to 4 meter, X2 is equal to 8 meter respectively. From the origin on the x-axis, it is on x-axis. It is on x-axis. So you can write the two masses, 2 point masses, 3 kilogram and 5 kilogram, which are at the positions 4 meter and 8 meter from the origin on x-axis located position of center of mass of the 2 point masses from the origin and from 3 kilograms. So you are asked to find out or to locate XEM from the origin and 2 from 3 kilogram mass. This is the question. Let me draw the diagram for this question. You can just go step by step. Actually, they have mentioned this is the x-axis and this is the origin O. Two masses. Mass by M1 and another mass is M2. The masses are at distances 4 meter and 8 meter from the origin. This is the position of center of mass. They are asking you to find out the position of center of mass from the origin. First case. This is the first case. They are asking you to find out the position of center of mass from the origin. Already we saw the 2 point masses are at the positions. X1 is equal to 4 meter. Here you can write once again. Given data is this one. Let me solve this. M1 is equal to 3 kilogram. M2 is equal to 5 kilogram. Position of the first mass is X1 is equal to 4 meter. The position of second mass X2 is equal to 8 meter. We need to calculate XCM. Right? And the center of mass can be obtained using the formula what we saw earlier. If the two masses are located at some distance from the origin, then for such a case, the formula to find out the position of center of mass is XCM is equal to M1 X1 plus M2 X2 divided by M1 plus M2. Here M1 is 3 kilogram, X1 is 4 meter, M2 is 5 kilogram, X2 is 8 meter divided by M1 plus M2, which is 3 plus 5. So if you take a product of this, 12 plus 40 divided by 8, which is 52 divided by 8, 6.5 meter is the position of center of mass from the origin. So XCM is equal to 6.5 meter. If you look at the case here, I can show you in the diagram. The center of mass is shifted, or center of mass is is located. Actually, this is the approximate position where I have drawn the center of mass. But the center of mass is at this particular position. I can show you here. This is the position where the center of mass is present. And from the result, I can say this is 2.5 meter from the mass M1 and 1.5 meter from the mass M2. And this result itself gives you the idea that the center of mass is located very close to the heavier mass. But we are asked to find out two cases, right? One is the position of center of mass from the origin. And second one, when the origin coincides with the mass M1, then what will be the position of center of mass from the 3 kilogram mass? From the 3 kilogram mass. So this you have to check out. This is 3 kilogram and this one is 5 kilogram. Now, we already finished the first case. Second case is that the origin coincides with the mass M1, which is equal to 3 kilogram. That's what is given in the second case. The second case, we are given the condition. This is the x-axis where the two masses are present. So this is the origin O, and the mass M1 coincides, or the mass M1 is there exactly at the origin, and the mass M2, which is equal to 5 kilogram, is at a distance of 4 meter from the 3 kilogram mass. From the 3 kilogram mass. From the diagram itself, we can understand. From the diagram itself, we can understand. I can go to the diagram once again here. If M1 is at a distance of 4 meter, M2 is at a distance of 8 meter, then the distance between M1 and M2, the distance between M1 and M2 is 4 meter. From the diagram itself, we can show it. See, the distance between M1 and M2 is 4 meter. So this is what I have mentioned here. If the origin coincides with the mass M1, then we can say the distance between the two masses M1 and M2 is 4 meter. M1 and M2 is 4 meter. Now you are asked to calculate the position of center of mass, that is XCM. Here in this particular case, from the diagram, we are getting the data that once again mass M1 is equal to 3 kilogram. There is no change in it. M2 is equal to 5 kilogram. M2 is equal to 5 kilogram. Actually, this is equal to M2 is equal to 5 kilogram. And then position of the first mass M1 is 0 meter because it is coinciding exactly at the origin. So X1 is equal to 0 meter. X2 is equal to 4 meter from the 3 kilogram mass or from the origin. You are asked to calculate what is the value of XCM. So we can find it out. We already saw in the formula that when the mass, any one of the masses coinciding with the origin, then the position of center of mass can be calculated with the formula XCM is equal to M2 X2 divided by M1 plus M2 if the origin coincides with the mass M1. If it coincides with the mass M2, then you can reverse the formula. Now we can see here XCM. Actually, this is X, not alpha. It looks like alpha. Can show you XCM is equal to M2 X2 divided by M1 plus M2. This is the formula you had come across. We are using the formula here. XCM is equal to M2 is 5 kilogram. Actually, when you substitute it in this way, you can just go step by step even. Even I can write M1 X1. M2 is 5 kilogram. X2 is 4 meter plus M1 is 3 kilogram. M1 is 3 kilogram. X1 is 0 divided by 3 plus 5. If you look at the case here, this is 20 plus 0. So I am not showing it here. divided by 8. So 2 8 are 16, 4, so 2.5 meter. So I can write here XCM is equal to 2.5 meter. So the position of center of mass from the 3 kilogram mass is 2.5 meter. The position of center of mass from the origin is 2.5 meter. And it is at a distance of 1.5 meter from the 5 kilogram mass. Once again, we can show here that the position of center of mass is located very close to the heavier mass. The position of center of mass is located very close to the heavier mass. Right? The center of mass is located exactly at 2.5 meters from the 3 kilogram point mass and 1.5 meters from the 5 kilogram point mass on the x-axis. The result shows that the center of mass is located close to the larger mass. And if the origin is shifted to the center, what happens? If the origin is shifted to the center, what happens? Then the principle of moment holds good in this condition. So we can show here if the origin is shifted towards the center. Actually, this is not asked in your problem, but let me show you that if the origin coincides with the center of mass itself, this is along the x-axis. This is the position of center of mass. Actually, this is the center of mass. Actually, this is a 3 kilogram mass. And this one is 5 kilogram mass. Then, if I say if the origin is shifted to this center of mass, actually it coincides with the center of mass, then what will be the case here? We can simply show here that the principle of moment holds good. Actually, in the previous class, you have come across this condition that the position of center of mass is 0, XCM is 0. If XCM tends to become 0 and X1 become negative and X2 become positive, then principle of moment holds good. You would have come across this condition. XCM is equal to M1X1 plus M2X2 divided by M1 plus M2. The position of center of mass becomes 0, and then X1 is along the negative direction because origin is here. So this will become minus X1. This will become plus X2, plus X2, plus X2. So M1 minus X1 plus of M2 X2. When you cross multiply this M1 plus M2, then that will also become 0. So you will simply have M1 X1 is equal to M2 X2. So as I told you, principle of moment holds good in this particular case. Principle of moment holds good in this particular case. So if you calculate principle of moments with the data, mass is 3 kilogram, X1 is given as 2.5 meter. We obtain the value that X1 is equal to 2.5 meter. So 3 into 2.5 meter is equal to 5 into 1.5 meter. So if you multiply this, you will have 7.5 and 7.5. So the product of mass and distance has the same value. So the principle of moment holds good. So we are exactly holding the object or the 2 point masses at its center of mass. That is what this condition reveals. If the origin coincides with the center of mass itself, what will happen? Principle of moment holds good. Also, you can compare the conditions, case 1 and 2, and you can easily find out the result that when you compare the case 1 with the case 2, the position of center of mass is 2.5 meter from the 3 kilogram mass can be easily obtained by subtracting 4 meter from the position of center of mass, which we have obtained in the first case as 6.5 meter. Right? When you subtract 4 meter from the position of 3 kilogram mass from 6.5 meter, you will get the center of mass which was located from the 3 kilogram mass. Actually, with the diagram, I can explain you clearly that if you look at the diagram, it's very simple. Look at the case here. From the diagram itself, we can say in the first case, the position of center of mass has been calculated as 6.5 meter, and the position of 3 kilogram mass is 4 meters from the origin. If you subtract 4 meters from 6.5 meter, what will you get? 2.5 meter. So the position of center of mass from the 3 kilogram mass is 2.5 meter. Right? Is it clear? If you want to calculate the position of center of mass from 3 kilogram mass, for which case? Second one, we can simply show it here that from the 3 kilogram mass, the position of center of mass is at a distance of 2.5 meter. That can be easily obtained from the first case itself. That if you subtract 4 meters from 6.5 meter, you will be exactly there at the 3 kilogram mass. So from 3 kilogram mass, the position of center of mass will be 2.5 meter. That is very clear from the diagram. So this is all about the problem what we discussed so far. Now we have to go for the second problem. So what do you understand from this problem? That is the question. Actually, whenever you solve a problem, you should not go with the numerical calculations. That won't help. What is the result we have obtained? That is important. So if you look at the questions, when the 2 point masses are from the origin, then the center of mass is located at a distance of 6.5 meter from the origin. When the same origin is located exactly at the 3 kilogram mass, the position of center of mass is at the distance of 2.5 meter from 3 kilogram mass. Both the results are same, but the measure of the distance is different. For the two masses, the center of mass is the same. It is located at the same point. And also, we can arrive at a conclusion that the center of mass coincides, or means center of mass is located very close to the mass which is of greater magnitude. So, what do you understand from this? You might have seen the farmers taking plow on their shoulders. Nowadays, you cannot see that. Farmers will be taking plow. அதாவது உழவு செய்யறதுக்கு ஏற்களை உயர்த்திக்கிட்டு போவாங்க. ஒரு end ஹெவியா இருக்கும், ஒரு end லைட்டா இருக்கும். நீங்க பாத்தீங்கன்னா தெரியும். They will support it on their shoulders exactly close to the point where the plow is present. எந்த end ஹெவியா இருக்கும், அந்த endல வந்து பாத்தீங்கன்னா support பண்ணுவாங்க. So that they can carry it very clearly because the center of mass lies exactly at that point. For another example, you might have seen people carrying water. But beam balance is the best design. Beam balance is based on this idea, principle of moments, last condition for the condition. And also, if you go with another example, you might have seen in the drought areas that people will be carrying pots, water pots, with the help of a beam supported like this. Diagrammatically, I can show it. This is a beam and a pot will be carried by the person. Whether the pot is bigger or smaller, whatever the condition is, he will be supporting it exactly at the center of mass. So he will be finding it at the center of mass. Suppose if this is a heavier one and this is a lighter one, then he has to hold it very close to this particular point because center of mass will be lying very close to the heavier masses. If this idea is required, whenever and wherever you are doing any physical work, you are asked to lift up any object, then when it will be very easy to lift and carry out is that when you hold it very close to, or when you hold it at the center of mass. How will you find the center of mass? See, this is the simple idea. If you know, actually this is on the calculation list. You can just approximate it easily. So if you carry it by holding it exactly at the center of mass, then it will be much easier to carry. So this is the idea related to the problem what we discussed first. Second one, for a uniform disk of, for example 5.2. Example 5.2. They are given, actually this is a big problem. For a uniform disk of radius r, A small disk of radius r by 2 is cut and removed as shown in the figure. Find the center of mass of the remaining portion of the disk. This is quite simple. Question is very simple. For a uniform disk of radius r, there is a uniform disk of radius r. A small portion is cut. A small portion of radius r by 2 is cut. Actually, total radius is capital R, as you know. This is the center O. This is the radius R. Actually, a small portion is cut over here. This is the remaining portion. Actually, this portion is the remaining portion. This is the remaining portion of the disk. Fine. Actually, this is the remaining portion of the disk. Actually, this is R by 2. This is what we have shown earlier. R by 2. Actually, they are asking you to calculate the center of mass of the shaded portion. They are asking you to calculate the center of mass of the shaded portion. Let me say the center of mass of the shaded portion is at a distance x to the left of the origin. Is at a distance x to the left of the origin. We shall go step by step. Fine. You can go with the solution here. Let us consider the mass of the uncut disk be capital M. Capital M be the mass of the uncut disk. Before you cut the smaller portion or small portion of the disk, the entire disk whose mass has been assumed to be capital M, and the center of mass will be exactly located at the origin. In this case, center of mass for the uncut disk is located exactly on the origin. So its center of mass would be at the geometric center of the disk on which the origin coincides. Actually, the origin coincides with the geometric center, so the center of mass is exactly at the origin. Let small m be the mass of the small disk which is cut. The disk which is cut. So small m will be the mass of the small disk which is removed from the larger disk, and its center of mass is at a position. The center of mass is at a position r by 2 to the right of the origin. To the right of the origin. You just look at the case here. It is to the right of the origin. So from the origin, it is at a distance. The COM is at a distance r by 2 from the right of the origin for this cut disk, the smaller portion of the disk. Its mass is a small m. Its mass is capital M. Actually, the total mass, combined mass is capital M. Combined mass is capital M. The left out mass, actually, this is M minus M. The total mass is capital M. This is how we have to take. Before you cut the smaller portion of the disk, or goes around the mass capital M, other or chinna portion, center road attach cut pandringa. அதுக்கான diameter capital R. அப்படி இருந்ததுன்னா அதனுடைய mass small m. Then the left portion of the dosa, அது வந்து பாத்தீங்கன்னா m minus of small m. This is the idea. For the entire dosa, the center of mass is at its origin. For the smaller portion of the dosa, the center of mass is at a distance r by 2 to the right of the origin. So idea is quite simple. Now we have to solve the problem here. That the remaining portion of this should have a center of mass at a distance x. So the remaining portion would have its center of mass COM of the remaining disk is at a distance x from the origin to the left of the origin, x from the origin and to the left of the origin. We have to find out what is the value of x. So we can write from the principle of moments. Why are you using principle of moments here? Idea is simple, that the origin coincides exactly with the center of mass, with the geometric center. So here principle of moments comes into play. You can write the principle of moments comes into play, that m1 x1 is equal to m2 x2. The formula is simple, m1 x1 is equal to m2 x2. So I am going to write the principle of moments for the uncut disk, sorry, for the left out disk and the smaller portion of the disk. Left out disk and the smaller portion of the disk. So by the principle of moments, I can write the left out disk has a mass m minus of small m, and its center of mass is coinciding or is there at a distance x from the left of the origin, and the small m be the mass of the cut disk. Its center of mass is at a distance r by 2. Its center of mass is at a distance r by 2 to the right of the origin. So I can write x is equal to m r divided by 2 divided by capital M minus of small m. We need to know what is the value of small m. If we know that, you can easily find out the value of xm or x. So to find small m, we are going to introduce an idea that sigma is the surface mass density. Sigma is the surface mass density, which is mass per unit area. Mass per unit area. If sigma is the surface mass density of the given disk, if we need to find out the mass of the cut disk, we can write here mass of the small disk that is cut, or mass of the small disk is small m is equal to surface mass density multiplied by area of the small disk. Area of the small disk. So this idea will give you the value of mass of the small disk. This is quite simple. Unit area mass இவ்வளோ அப்படின்றது sigma சொல்லும். அப்போ இந்த ஏரியாவுக்கான mass என்ன? That will be obtained easily. Could you able to get the concept here? If sigma is the mass per unit area, unit surface area, then for this area of the small disk, sorry, for this area of the small disk, what is the mass? That is taken small m. So idea is simple. ரொம்ப சிம்பிளா சொல்லணும் எப்படின்னா, ஒரு சாக்லேட் 1 ரூபாய் அப்படின்னா 10 சாக்லேட் 10 ரூபாய். அது மாதிரி ஒரு யூனிட் ஏரியா ஆஃப் கிராஸ் செக்ஷனுக்கான மாஸ் சிக்மால சொல்ல முடியும்னா, இவ்வளவு ஏரியா ஆஃப் கிராஸ் செக்ஷனுக்கான மாஸ் என்ன? மல்டிப்ளைட் வித் தட். m is equal to sigma into area of the small disk. So small m is equal to sigma is capital M divided by pi capital R square, because this is the area of the large disk. M divided by pi capital R square. This is the value of sigma multiplied by area of the small disk. Area of the small disk is circle. So pi R square. As the radius is R by 2 for the small disk, we can write pi R by 2 the whole square. So small m is equal to m by pi r square into pi r by 2 the whole square. If you cancel this pi and then can cancel this pi over here, and then also you can write cancel r square and r square. What is left here is that you have capital M divided by 2 square is 4. This is left. So small m is capital M divided by 4. So mass of the small disk which is cut is 1/4 of the mass of the larger disk. So you found the mass of the small disk. So mass of the small disk is 1/4 of the mass of the larger disk. Now you just make this as equation number 2, and then you make the other one as equation number 1. To make this as equation number 1. So if you substitute 2 in 1, you will get the result that you have x is equal to small m divided by m minus or small m into r by 2. This is what you have in your expression, right? So I can write small m is capital M by 4 divided by capital M minus of capital M divided by 4 into r by 2. So can cancel this m by 4. M minus of m by 4 is 3m by 4. So m by 4 divided by 3 capital M divided by 4 into r by 2. So this m by 4 cancels out. You will have r by 6. So x is equal to r by 6. What does this indicate? We can simply say, what is this x? Actually, this is the distance of the center of mass of the left disk, or the disk which is cut. And it is to the left of the origin. So we can conclude that the distance r by 6 indicates here is that the position of the center of mass of the disk which is cut is at a distance of r by 6 to the left of the origin. R by 6 to the left of the origin. So I can show it here that this x is equal to r by 6, which indicates that this distance of center of mass from the origin is at a distance of r by 6. If the radius is capital R, the center of mass of the disk which is cut is 1/6 of the radius. 1/6 of the radius. So I can say if this radius is, let me say 6 meter, then x will be equal to 1 meter. That's the idea. X will be equal to 1 meter. To the left of the origin, that is important. To the left of the origin. So if you want to support, if you want to hold the cut disk with your finger, then you have to hold it exactly at the center of mass so that it will be kept balanced. And where you have to keep your finger, idea is simple, at a distance r by 6 from the origin, to the left of the origin. So this idea gives you, or this problem gives you a clear picture over here, that where the center of mass of this kind of disk will be located. Also, there is a question asked in your text that what will happen if a small portion of the disk is cut exactly at its center. There is a question. If this is the entire disk, what happens if it is cut exactly at the center? So at the center, if you cut it exactly at the center, what will happen to the center of mass? So answer is center of mass remains unchanged. Center of mass remains unchanged. Why? This entire disk is supposed to be made up of so many number of concentric rings. So if you assume large number of rings, one placed inside the other, you will be getting a disk. It is similar to that of a sliced onion. If you cut an onion in the shape of a circle, you can see that it is said to have layers which is in the form of concentric circles. So all the circles will have the same origin. So if you cut a smaller disk or a greater disk like this or further greater disk like this, whatever the shape of the disk doesn't matter, or whatever the portion or position where the disk is cut, thing is simple. The center of mass will be left unchanged, it will remain unchanged. In the sense, the disk is made up of so many number of concentric circles. So if you remove large number of circles from the disk, then also the center of mass will remain in its same position. So this is the answer for the question what is asked in your textbook. What will happen if the small disk is removed concentrically from the larger disk? See the statement. Concentrically. That condition is very important. You have to remove it concentrically. Then the center of mass will be remain unchanged. It will be exactly at its center. That is the meaning. The center of mass will be remaining exactly at its center. That's the result. Then we shall go on to the next problem. Example 5.3. Shall go for the next problem, example 5.3. The position vectors of 2 point masses 10 kilogram and 5 kilogram are minus 3i cap plus 2j cap plus 4k cap meter, and 3i cap plus 6j cap plus 5k cap meter respectively. Locate the position of center of mass. Locate the position of center of mass. Actually, if I show it to you diagrammatically, then the idea will be very simple. Actually, what is given is that mass M1 is 10 kilogram, mass M2 is 5 kilogram. Their position vectors are, I can say R1 vector or R1 cap even. Can write R1 vector is equal to minus 3i cap plus 2j cap plus 4k cap meter, and then R2 vector is equal to 3i cap plus 6j cap plus 5k cap meter. Actually, these are the position vectors. Let me draw the diagram for this. Diagram seems to be somewhat typical, but you can understand it clearly. So let me draw the coordinate axis over here. Let me take this as x-axis, this one as y-axis, and this one as z-axis. As you are given a negative sign for the x direction, for the x coordinate, I can take it as actually this is the origin, this is the negative x direction. So mass M1 is 10 kilogram, M2 is 5 kilogram. The position of the mass M1 is at 3-3i plus 2j plus 4k. So I can write, actually this is minus 3i cap. Let me say 1, 2, minus 3i cap. Then 2j cap, 1, 2. So to j cap, and then 4k cap. This is the position where 1, 2, 3, 4, 4k cap. So actually this is the position of 10 kilogram. This is how we have to draw, and from the origin. So this is R1. So position vector of R1 vector. This is the position vector of 10 kilogram mass. 10 kilogram mass. And where the 5 kilogram mass is present. Same 3i cap. So this is 3i cap. Actually, this is 2j. And this one is 4k cap. Now, this is 3i cap plus 6j cap. 1, 2, 3, 4, 5, somewhere over here 6k cap, and then 6j cap, and then 5k cap. This is 5k. So I can take it like this. Draw. This is the point where you have the 5 kilogram mass is present, and this is the position vector. This is the position vector R2. This diagram seems to be somewhat complex. This is not actually complex, it's very simple. Actually, this is a diagram which indicates that the two masses, 10 kilogram and 5 kilogram, are at these positions. Right? You are asked to find out what is the position of center of mass. Center of mass. That you have to find out from the origin. So, what is the position of center of mass of these two masses, 10 kilogram and 5 kilogram? This is how the position of the masses are present. So, you can simply calculate the position of the center of mass over here. Actually, this is a three-dimensional case. That is why we are going for R vector. If it is for x direction, you will be writing I cap. Y direction, j cap. Is the direction k cap. If it is in space, then you have to go with R vector. So R vector indicates the position vector. So you are asked to calculate what is the position of center of mass from the origin. See, this is the red line which indicates the position of center of mass. So I can write here R vector is equal to M1 R1 vector, because we have the 10 kilogram mass in the space, right? In the space, which is given by the position vector R1 vector. So M1 R1 vector plus M2 R2 vector divided by M1 plus M2. That's all. M1 plus M2. Let me do the calculation here. M1 mass is 10 kilogram multiplied by R1 vector is given. Actually, from the diagram, I can write minus of 3I cap plus 2J cap plus 4K cap plus mass is M2 is 5 kilogram and its position vector is 3I cap plus 6J cap plus 5K cap divided by 10 plus 5. Divided by 10 plus 5. We just simply multiply the given value here. What will we get? Minus 3 into 10. So minus of 30 I cap plus 20 J cap plus 40 K cap plus 5 into 3, 15 I cap plus 30 J cap plus 25 K cap divided by 15. So you just add the I vector, J vector and K vectors separately, so that minus 30 plus 15 will become minus of 15 I cap plus 20 plus 30, 50 J cap plus 40 plus 25, 65 K cap divided by 15. So if you divide this value, by 15, then you will get 15 divided by 15 is 1. So simply minus I cap plus 50 divided by 15. It is 10 divided by 3 J cap plus 65 divided by 15. So 13 divided by 3 K cap. 13 divided by 3 K cap. So minus I cap plus 10 by 3 J cap plus 13 divided by 3 K cap meter is the position of center of mass. Is the position of center of mass of the 2 point masses which are located at the positions R1 vector and R2 vector respectively. So the center of mass is located at the position R vector. Very simple idea, but you should understand how the masses are present. That is important. The 10 kilogram masses, they are in this particular portion, minus 3A plus 2J and minus plus 4K gap. And 5 kilogram masses at a distance of 3A gap plus 6A gap plus 5K gap. So where the center of mass is located, this red line indicates the center of mass, which is minus I cap plus 10 by 3 J cap plus 13 by 3 K cap. That is the position where the center of mass can be located. Even in a simple way, we can write minus I cap plus of 10 by 3 is 3.3. I'm just approximating it. 3.3 J cap plus 4. Almost 3. So 4.3, 4.3 degree, almost 12.9. So 4.3 K cap. So this is the position where the center of mass is located. So if you want to represent it in the diagram is a bit messy, but let me show you where the position is. So it is shifted towards the 10 kilogram mass. You can see here. The center of mass is shifted towards the 10 kilogram mass. That's why the diagram is shown like this. Actually, I have shown it here like this. It is minus I. So this is the position minus I plus 3.3 J. So almost 3.3 J. And then 4.3 K. This is 4.3 K. So if you project it forward, so it is at this particular position. Minus I plus 3.3 J plus 4.3 K. Actually, in this diagram, I cannot show it because this is a 3-dimensional diagram. I am showing it in a 2-dimensional space. So it is a little bit messy, but it is projected in the forward direction. And we can say this minus I cap indicates that the center of mass is shifted towards the negative x direction. That means it is shifted towards the greater mass, right? So it is very well understood that the center of mass is always located towards the mass with the greater magnitude. That's all, right? So this is all about the problem which we discussed related to the center of mass of 2-point masses. We shall have the discussions afterwards. Tomorrow we will discuss with the other areas. I would like to stop at this point. Thank you.